Higher order derivatives. So we're going to, okay, we'll talk about that in a minute. We're going to start by just talking in general about derivatives. This unit, the last unit had no like word problems, no applications. We did some problem solving, but that was just finding equations of lines, that sort of thing. But there were no word problems in the last unit, right? And in this unit, there's going to be a lot. We're going to do a lot of days this week of doing some problem solving and like word problems and that sort of thing. So we're going to get back into the swing of thinking about what functions represent, how they represent things, how we solve problems with them, and so also like what derivatives, how they factor into that, how we can use derivatives to solve problems, how they give us more information. So we're going to start trying to think about that today. So if I have this graph, okay, we're just going to chat a little bit and think. So I don't know, you don't really have to write any of this down, I don't think. Let's say I have some kind of relationship like that, and I'm just going to say that it is, that's the equation of that line. Does that look about right? Okay. And that would mean that the derivative would be what? So 100 times x to the 1/2. Bring the 1/2 down, multiply by 100, so that's going to be 50. Is that right? And then x to the negative 1/2, so 50 over the square root of x. Is that about right? You okay with that? So this graph is representing cost, total cost, depending on the number of people. I don't know what it's for. Maybe it's for like a venue, like a banquet hall or a restaurant, or I don't know. Movies, could be anything. So what I just want to look at, and what I think can be interesting, is if we sort of look at the table of values. So if x is 1, 100 times the square root of 1 is 100 times 1, so it's 100. What does that mean? One person costs $100. And then 2, 100 times the square root of 2, so I did that on my calculator, it's 141.42. 3, 100 times the square root of 3 is 173.21. And 4, 100 times the square root of 4 is 100 times 2 is 200. And then I could add another one here. Let's do this. So before we do that, what is, like, think about those numbers. What does that mean, or what do we see is happening here? I'm going to move this over. It costs a lot for the first person, but it's not as much per person afterwards. Do you see that in the pattern there? So if I was doing, like, remember we call this first differences. We can do first differences, second differences. This is an increase of 41.42. This is an increase of, what about, sorry, not 141, 41. Of about 30. 173 minus 141, whoops. Right? So approximately 30, 32. And then this is approximately 27, something like that is the increase that's happening there. So it's increasing by less each time. And what I'm thinking about is, how is that represented in the curve? And then if I evaluate the derivative at those points, 50 divided by 1 is 50. 50 divided by the square root of 2 is 35.36. Divided by the square root of 3 is 28.87. And 50 divided by the square root of 4 is 25. So what does the derivative represent in this case? When It's the instantaneous rate of change. And rate of change is like a rate, so the cost per person. But it's the instantaneous cost per person, which is a strange thing. Like in a real life situation, I care that 4 people costs $200. I wouldn't necessarily care that it's changing, that it's $25 per person, or changing by $25 per person at that moment, but that's what's happening. Does that kind of make some sense when you think about that? I think that's important, to remind ourselves. So we're going to do some specific word types of problems today involving movement, but graphs can represent different things, and it can be hard. It's going to be easy to think of what they represent today, but a little bit harder to think about what they represent in other situations like cost per person, that kind of thing. So anyway, this is dollars per person. That, I guess it's strange to think, like, if I paid $200 for 4 people, I paid $50 per person, but the derivative is telling me I'm actually paying $25 per person at that point. Do you see what I'm saying here? But the reason is because I paid a lot for the first person, so I am kind of paying less per person later on, right? But you would maybe only care about because you would average it. We tend to average it, and so if I plot this point at 4, let's say, and this is 200, you would take the average, right? You would average the total cost over the 4 people, but what you're actually paying at that point comes from the derivative. Anyway, this, again, just kind of thinking about these things, like getting back to what is the derivative. We did all these skills in the last unit, all this work with algebra, and we're getting back into what does it actually mean. So there's one graph. Here's another one. We're not going to do as much work with it, but degrees Celsius. So I guess it would just be like the degrees Celsius over, well, that was kind of a strange line, over time, or degrees Celsius per hour, right? That's another rate that could be represented. And the derivative would give us how it's changing at a particular moment over the course of the day. Maybe you'd look at, I don't know. Okay, so now we're going to talk, before we move on to doing some actual problems, we have to do a little definition. It's a really simple definition. What is the second derivative? It's when you take the derivative of the derivative. That's it. Just like you do first difference and then you do second differences. And second differences is finding the differences between the first differences, right? So derivative, same thing. And of course, you could take third and fourth and fifth. You could keep going. So very quickly, again, I'm not really sure you need to write all this down because you should be able to do this. You can look at it later if you want. And I'm going to go through this quickly because it's not very interesting compared to what we're going to do next. So if I take the derivative of this expression, that looks like negative 30x to the 5. And then this is like x to the 1/2, right? So I multiply by 2, I get negative x to the negative 1/2 plus 7. Does that look right? And then if I take the second derivative, here we go for the first time, we just do like a double prime. 5 times negative 30 is negative 150, x to the 4th. So we see that the exponent's been reduced twice, right? And if we think about the degree of a polynomial function, when you take the derivative is lowered by 1, so you take the second derivative, it's going to be lowered by 2 from the original function. Like, that's a pretty clear pattern. And this becomes plus 1/2 x to the negative 3 over 2, and the derivative of 7 is 0, so that's gone. That's it, right? If this is dy by dx, we call this one d squared y by dx squared. That's the notation there. Yep. Yes. Exactly. Mm-hmm. I'm not sure I know the answer to that. It's kind of just a notational thing. It probably has something to do with, you know how we talked about this the other day, and in fact, we talked, when we did implicit differentiation, we sort of realized that when we take derivatives, we actually take derivatives with respect to a particular variable. So I can't, like if I have a multivariable statement, like with A's and B's and C's and D's, if I take the derivative, you pick one variable that you're taking the derivative with respect to that variable. And that's what goes on the bottom. It probably has something to do with that. But it doesn't really matter, I don't think, for us. Okay, let's try one more. What would it look like if I was doing something like this? Oh, so f prime of x. Bring the 3 down, multiply by 6, so I get 18 x squared plus 4 all squared times the derivative of what's inside, so times 2x. And I would probably want to simplify that, so I'd get 36x x squared plus 4 all squared. And then if I want to take the second derivative, now I have to use product rule. So the derivative of the first thing is 36 times the second thing plus the first thing times the derivative of the second thing. So that's going to be times 2 times the derivative of what's inside, x squared plus 4 to the 1 now. And then again, just kind of cleaning some of that up. This is all just using, there's nothing different here. Like when you take the derivative a second time, you could ignore the fact that you took it a first time. It's got nothing to do with, right? We're just taking the derivative of a new expression. So it's not, doesn't change in any way. And let's see, I think this works out to 144x times x squared plus 4, something like that. X squared. Ugh. Okay, that's all. So kind of a notation thing, no new skill there, but now we know that there is such thing as a second derivative. We okay with that? Let's skip this question. It's not very interesting. So all it's saying is like, yeah, we could find places in the second derivative, like find y double prime or the second derivative when x equals 0, find the value of the second derivative. That's all. Okay, not very interesting. This is a little bit more interesting. So we talked very briefly about those two kind of applications that you might see of functions changing cost over time, or cost for a number of people, or temperature over time. What is change in distance over time? What is change in distance over time? Speed, right? We've got a word for that, rate. That's an important rate, and that's one that we are very comfortable with. It makes a lot of sense that, and in MHF and even in this course a little bit, when we talk about average rate of change versus instantaneous rate of change, changing distances over time is a nice one because it's like intuitive and it makes sense, and we can talk about the average change in distance over time, or the instantaneous change in distance over time, all those kinds of things, right? We've talked about all that. And then here, so hold on, what's this then? Change in speed over time is what, John? Acceleration, if you've taken physics, which I know many of you have, or are taking out, you've done a lot with this. So this is not something new or interesting, but if I have a function that represents distance over time, so the graph of that function represents distance over time, the derivative of that function, which finds the instantaneous change, rate of change of distance over time, would be speed, right? And then if I take the second derivative, what would that function be? Well, it would be acceleration, right? So this is really useful that if I have a function, the derivative of that function in this case, in other cases it would mean other things, but like I said, in this case with movement, it's really easy for us to kind of connect to. It means something really specific, speed or acceleration. Okay, so now let's take a look at an interesting question. Okay, so we've got this function that represents the motion of a particle, some object, some particle. And so this is the distance function, because s is distance in meters, t is time in seconds. So if I find the derivative of this, that will be the velocity function. And so that's going to be 3t squared minus 18t plus 15. And if I want to find the acceleration function, that's going to be s double prime. Oops. So the second derivative, or the derivative of the velocity function, right? The first derivative of the velocity function. And we'll give that a new name, a at t, and that's going to be 6t minus 18. The whole point of mathematics is that we can use it to model things that happen in the real world and then make predictions based on that model, or, plan for expected outcomes, or whatever it is, or design something to work a certain way. But we understand more about what's happening. The more math we can do about it, the more information we can get out of it. We just know more about it. So if I know a function, if I have a function for the distance that an object's traveling, and I can then use that to figure out its velocity or its acceleration at particular times, that's very, very useful, I think. Right? So that's the idea. So it's nice to remind ourselves of like what the whole point of all of this is. And then we can start answering questions. So at what time is the particle at rest? And so here's where, okay, I've got all these tools, I've got these functions that I can get a lot of information out. Which one do I want to use? What's this actually asking? What do you think? When is the particle at rest? What's that asking? John? So v at t equals 0. So I go up and I get my velocity function, 3t squared minus 18t plus 15 equals 0. I can factor out a 3. Therefore, the particle is at rest when t equals 1 and 5, or at 1 second and 5 seconds. Simple enough. When is the particle moving in a positive direction? So if we think of this particle, could be sort of moving back and forth in a straight line. And if I'm going to your right, or to my right or whatever, that's positive, like on a number line. And to the left would be a negative direction. Again, if you've taken physics, you've talked about, like, velocity has can have a direction, right? So when is the particle moving in a positive direction? What is this question? How would I use math to solve this? The skills that we've learned over our entire mathematical career, but I'm thinking especially like last semester and so far this semester, we've got all these skills now. How do we use it to solve a problem like this? Anybody? What do you think, John? Nice. So when the velocity is greater than 0, when it's a positive, when velocity is positive, what does that mean? Bigger than 0. This is something we know how to solve. We've done inequalities. So again, I go back up to my, and I'm going to pick this one because it's already done. If we graphed that original cubic function, unfortunately, I think it doesn't factor nicely, but I think it looks something kind of like this. And then when we graph the quadratic, so we're going to do that here, just kind of sketch it. Let's think about this quadratic. So it's got x-intercepts at +1 and +5, and it's opening upwards. Is that right? This goes all the way back to, again, MHF, or even before that, when we know things about quadratics. I don't care about the rest of it, but I know that it goes like this. Does that make sense? So when we solve polynomial inequalities, we think about the graph, right? We use the graph to our advantage. So therefore, the particle is moving in a positive direction from 0 to t less than 1 and t greater than 5. I'm not sure I can fit it on my graph, but the domain of this function in the real world, x is an element of the real numbers such that x is greater than or equal to, or t, I guess it should be. Let's change that to t. Such that t is greater than or equal to 0, right? Because that's time. Time started at 0. It doesn't go back to the negative. So although that parabola would go into the negatives, our time wouldn't. Isn't that true typically? We're talking about these situations. It starts at t equals 0. So that's why it's moving in a positive direction starting at 0, not just less than 1 and greater than 5. Does that make sense? Any questions so far? Are we okay? feel like it got really quiet all of a sudden. Okay. For what times is the acceleration positive? So this is similar. Why don't you go ahead and try this one? It's the algebra is pretty simple. So we got to go back and get our acceleration function. And when is that positive? And I believe it was 6t minus 18. Is that right? Okay, so again, going back and thinking about these functions, now that is a linear function, so we could graph that as well, right? Here's our quadratic velocity. And again, this was 1 and this was 5. Halfway between 1 and 5, 3. What happens at 3? Is when the velocity starts turning up, and so you can see that the slope of the tangent would be positive there, and that's where my acceleration function is going to be positive. Does that make sense? See how it all relates? Like, it's really important to think about how each one of these functions relates to the others, what it tells us about the others. Okay, any questions? I'm going to do... Oh, we got one more here, actually, one more interesting question. Sketch the path of the particle for the first 10 seconds. Find the total distance traveled. This one can be a little bit tricky, I think. When you have to do this in the practice or if you have to do it on your own, but it's an interesting idea. And you may have done something like this in physics. I'm sure you've sort of done these kinds of things at least. So what we want to do to be able to sketch the path of the particle for the first 10 seconds is we understand, with all the information we've already got, we know a fair bit about what the particle's doing. And we can think about the graphs and the behavior and like end behavior and functions in general. And then we can sort of make some conclusions about what's happening with this thing. So we don't have all the information we need a little bit more. So we want to find where the particle is at the very beginning. So I just plug that into that original function and everything goes to 0 and I just get 24, right? The original distance function. Something happens at 1 second because something interesting happens to the velocity at that point. So let's figure out where the particle is at 1 second. So I just plug that into all the values. So 1 cubed minus 9 times 1 squared plus 15 plus 24, and I get 31. I want to figure out what happens at 5 seconds, where it is at 5 seconds, because that's where something interesting happens to the velocity again. And I believe it works out to -1. And I'm going to do 6 to sort of figure out what's happening next. And the distance at 6, these are all in meters. And then I'm going to do 10 as well, and that works out to 274. So these are the kinds of questions to build a full picture. We need to know, where does it start? Where and when does it stop or like turn around? So it's changing direction when velocity is 0, because it's going this way, slowing down, stopping for an instant, and then going back the other direction, right, when velocity is negative. And we can think about the function to figure that stuff out. What direction is it going? Where is it going? So in between all those important, in between and at the end as well. Okay, so let's see if we can do this. I'm going to start, and looking at my numbers, I'm going to start up here at 24. So we've got positive velocity from 0 to 1, and I get to 31. Then we've got negative velocity, right? All the way to 5 seconds. So I'm going back this way, and I end up at -1 meter. Then we've got positive velocity again, and we know that, like the end behavior of the function, we know that it's accelerating, and we know that its velocity is positive forever after that, right? So let's see. It goes something like this. It goes this way, and then like that, forever. 274 is like way off the page, but the arrow kind of shows. So this is, I should have my, so t equals 0, t equals 1, t equals 5. And I checked, like the reason why I checked 6 is I just kind of want to see what it's like, sort of about where it is, I guess, after. Like I know that it's going to keep going that way, but it's good to sort of check a value here or there. So at t equals 6, we're at 6 meters, and then we go on forever. Does that make sense? Now this particle is, I think, actually moving in a straight line. It's not moving in a curved path, but the curved path sort of can show instead of like I would have to do this and then back that way to -1. You know what I mean? So that's why we do a curved path, but it's actually moving on a straight line. Makes sense? Any questions about that? And I'm not sure it's on here, but one more thing I want to look at is what's the total distance that it traveled in those 10 seconds? So not what's its final, this is a bit tricky, because if we want to know the distance that it's at, I would just plug 10 in. We already did that. Plug 10 in to the function and get 274. That's its location. But how much distance has it traveled in that time? So how do we find that? We're going to add up all the distances that it traveled. So it went from 24 to 31. So let's see, total. So F is total distance for 10 seconds. So from 0 to 1 second, it is 31 minus 24. That's the distance that it traveled, which is 7, right? From 1 to 5 seconds, what distance did it travel? It ended at -1 and it started at 31. So -1 to 31 is going to give me a negative, but I don't want to subtract that distance. I want to add it. So when we're talking about a magnitude. It's like we're taking the absolute value. The form here is not really super important. This is not like a formal process that we're doing. So this works out to positive 32. I just want to make sure that the numbers are all positive. I traveled backwards, so that value would be negative, but I want the actual magnitude of the distance. So that's what absolute value does. Or you could subtract the other way. You could do 31 minus negative 1, and you'd still get 32. Does that make sense? And then this looks awkward, so I'm going to turn that into 1. And then from 5 to 10, again, we end at 274 minus negative 1 is 275. And if I sum those three numbers, we end up with 314. Okay? So total distance. Total is when you add up all the make sure they're all positive. These are some of the kinds of questions you might be asked when you're doing these kinds of movement problems, but there are others, right? So some of what we're doing today is, and in this unit in general, is like, how do we use, which function do I want to use? Am I setting it equal to 0? Am I doing something else with it? Again, just getting information out of the problem. Tomorrow we do a little bit more of like examining a new skill. We already have the skill, but what information is the skill we have? What is it? What can it tell us? And then after that, like I said, more kind of word problem things that are going to be different from this, from movement, but applying it in other ways. Okay, let's do another one. Mr. Belair is fired out of a cannon. In my spare time, I'm a daredevil. It's true. Okay, so you can go ahead and start by getting the velocity function and the acceleration function. So take the derivative and the second derivative. And then we're just going to answer a few questions, and it's the same idea, like which function we want to use, what are we doing with the function, how do we answer these questions. What did you notice about the acceleration function? Why would that be? Does that make sense? John, what do you think? Yeah, very good. So thinking about the degree, that's what's going to happen. What else? So think about that. Where are the physics people in here? What is negative 10? Jason? Yes, good. It's the mathematical version of 9.8 meters per second. We like to round things in math class, so sometimes you'll see like the negative 5 t squared or negative 5x squared is like a rounded version that gives us a negative 10, but it would actually be negative 4.9. But even that is kind of rounded, right? Like that 9.8 is rounded. It depends on where you are relative to the planet, that kind of thing. But anyway, yeah. So it makes sense because it's gravity. That's our gravitational constant. What was the starting height? So this is the vertical intercept. This is just when the height equals 0, or when s or at t equals, sorry, not when the height equals 0, when time equals 0, what is the height? And in this form, I know that it's just that, right? So in standard form, it's kind of nice. So s at 0 equals 1. So 1 meter. When is Mr. Belair at rest? Again, what does that mean? When your velocity is 0. So find our velocity function. Therefore, he is at rest at 3 seconds. I'm not going to do a therefore statement for every one of these because they're all kind of boring, but what is his maximum height? This is an interesting question. How are we going to answer this one? John, what do you think? Would be what? So the starting height is 1 meter. You're saying that's the max height? Right. Interesting. Except that I think, does anybody else have anything they want to add to that? Any thoughts? What kind of function is this? Parabola, right? So the maximum, and it opens downward, so the maximum is going to be where? What's the maximum of a parabola? At the vertex. Where does the vertex occur? When the derivative is 0, when he's at rest, like I'm picturing shot out of a cannon, gets to the top, that's where he's at rest. I'm at rest, I guess. And then starts coming back down. And that's positive. We already figured that out. That's when t equals 3, right? So it seems to be that there's that acceleration is negative, but the velocity starts out as positive. So the velocity is going up and then is just accelerating or decelerating or accelerating downwards the whole time. Okay, so now what we're going to do is we're going to say v at 3, right? No, s at 3. What is the maximum height? The height, which is s at 3. So -5 times 3 squared plus 30 times 3 plus 1. Where's my calculator? What does this work out to? Does anybody have that? Jason? 46. Sounds about right. Blah, 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 blah. 46 meters. I believe it was in meters. Oh, it didn't tell us. We'll say it's meters. When is Mr. Belair higher than 41 meters? So it gets above 46. This is my graph here is terribly out of scale, but so start at 1, and if this is 41 meters, when am I above 41 meters? So how are we going to figure out that one? Well, again, this is asking about distance. You might, when you're asked a question, in your head you might say, this question is asking me about speed. This question is asking me about acceleration. This question is asking me about distance or height or something like that. And that will tell us which of the functions we're using. So when is greater than 41? So negative 5t squared plus 30t plus 1 greater than 41. Minus 40 is greater than 0, right? How do we solve an inequality, polynomial inequality, or any other inequality? We're going to group everything to one side, have it be equal to 0, 0 on the other side. Factor. So what is this telling us? Now this is, again, interesting. This function here, negative 5t squared plus 30t minus 40, is a quadratic again. But it's not the original quadratic that we started with, right? It's a different one that because we added in the 41. But it's still quadratic. But apparently it still opens down. And apparently it has intercepts at 2 and 4. So again, I'm using my understanding of the graph to answer the question. Therefore, Mr. Belair is above 41 meters between 2 and 4 seconds. And our last question, are we okay with this so far? Pretty simple algebra so far compared to what we were doing in the last unit. When does Mr. Belair hit the ground? So the unfortunate splat that happens right there. So how are we going to find this? Again, by factoring our original function. Negative 5, well, so s at t equals 0. Or maybe by factoring, maybe not. So this is negative 5t squared plus 30t plus 1 equals 0. And let's just check this. B squared minus 4ac is 920. Oops. So not factorable, but certainly solvable. So t is going to be just a reminder. We talked about this in the last unit, but we didn't actually do it, I don't think. But often when we're doing applications, the quadratic formula is going to show up and be needed because not everything's going to work out nicely. And I get two answers, negative 0.03 and t equals 6.03. And this one's obviously inadmissible. Therefore, Mr. Blair hits the ground at 6.03 seconds. Takes you all the way back to grade 10, solving little questions like this, right? But we can do a little bit, we understand it in a different way. A lot of what we did there is just grade 10 stuff, but we do understand quite a bit more about it. And what's interesting to me, there's a nice little comparison here about what happened here, that I got a negative answer that was inadmissible and a positive answer, and thinking about that graph, and then comparing that, contrasting it with this one where I had two positive answers, and just thinking about what it was we were solving. We kind of were like two slightly different quadratics, right? And how you can get different kinds of answers, but it's in the interpretation where everything really comes out. Any questions about any of that? So there's your practice. The only other thing I would encourage you to do is really to think about what does the derivative of a function tell us about the original function. So when we're setting the derivative equal to 0, or when we're finding, or something along those lines, what is that telling us about the original function? Really spend some time thinking about that, and then what does the second derivative tell us about the derivative or about the original function, that sort of thing as well. In the context of an application, absolutely, but then also just from a function perspective.